Good evening. I hope you can see my screen. Can you see my screen? Okay. So I think I'm audible also. Okay, we'll quickly start the session. So I'm going to take the tutorials for this course. So there will be 3 tutorials total for a single session. So this is I think tutorial number 2 or 3. Okay. So I am Ajay. So I'm doing my PhD at IIT Madras in the area of power electronics. So basically, we also deal with the control systems in power electronics. So I will go through what is covered in the course. Then I will go through previous year questions or previous semester's questions and a few questions that I've added so that we get more clarity on type of system that we have studied here. Okay, and anything you want to ask, please ask. Okay, so I'll wait for a couple of minutes so that a few more people can join. So I think notes for this course is available. So you can download those notes and whatever you want to add, you can add here itself. Okay, so I'll go through what has been taught in the first session. Okay, or the first week. So we are covering this topic. So this is actually being taught by engineering design department at IIT Madras Control Systems. So if you are from chemical engineering or electrical engineering, mechanical engineering, so that would be very useful to you. So this is the basic control system course, obviously. So we studied about what is system here. Okay, the definition of system exactly, or what it is called in different uh, engineering, like process if you are in chemical engineering, system or plant if you are from electrical or mechanical engineering. Okay, so this we'll be dealing with the dynamic system. So here time is the independent variable. So our system is a system or our input is changing with respect to time. Okay, or all the variables that are associated with the systems are function of time. Okay, okay. So mathematically, what is important is you want to map the input to the output. Okay, so this mapping is, so this is very important. Where in the first, I think, few weeks we'll be deriving mathematical equation for this system or plant here. So this is called mapping of input and output. Okay, so then we classified the dynamic system based on different first based on input, so CISO and MIMO. So single output, single input, single output, and multiple input, multiple output. Okay, so you can see here input and output both are function of, or they are real numbers. Okay, this time is also real. And we also covered what is linear and non-linear system. So in this control system, we are going to deal with a linear system, but if you see around in the real life, all the system, mostly the systems are non-linear. We try to linearize it or we get the linearized model of that plant so that we can model it better and we can study it better. Okay, so what does this how the system is defined as linear? It should follow the superposition principle. So what is the superposition principle? So if you see here, so basically two principles they have followed here. Okay, this is additivity and second one is your scaling. Okay, and here they have combined together. Okay, so if you just combine two inputs here, so the output should be combination of the output. So if u1t is the input to the system, y1t is the output, and again if another input is y2 of t and its output is y2 of t, if we combine u1 of t plus u2 of t, then you should get y1 t plus y2 of t. Okay, and if you scale any of the input, then you also should get the scale version of your output. So that is depicted here in second part here. Okay, so you can combine both here. Okay, so then we studied about the time variant or time invariant system. So here also mostly our systems, normal real life systems are varying, but we'll study the time invariant system. Okay, so a time invariant system is one that provides the same output for the same input irrespective of when it is applied. Okay, when the input is given. So you can see here example, red example and the blue green example here. So in the green one, we have just displaced the input by this time period t here. You can see it is delayed by this time t, and you can see the output is also delayed by t. So this system is time invariant system. Okay, so we'll see the examples. Okay, how to study whether the system is time invariant or not. Okay, mathematically you can prove it. So basic definition is this. Second, another definition, another classification of system is causal and non-causal. The causal system is one where the output at any point of time depends only on the past and current inputs. So it should not depend on the future inputs, right? So it is non-anticipatory system. So whatever the system that you see in real life, those are causal systems, okay? Because they only depend on past input and the present inputs or the outputs. Okay, they do not depend on future values, right? So these systems are non-anticipatory. So we cannot predict those values based on the inputs. So if you see anticipatory system is we can predict the future outputs based on past inputs and present input or output. Okay, so it's like example of weather forecasting. Okay, where you are forecasting the weather based on the past data. Okay, but that system, that anticipatory system may not be causal. Okay, because you need future input and we don't know the future input. Okay, so basically, so this term you're going to hear many times in this course. So LTI system. Okay, so we are going to study LTI system, linear time invariant system. So we have studied linear versus non-linear, SISO, MIMO, and time invariant and time varying. Any doubt in this three basic definitions? Because all the system that we are going to cover in this system in this course are going to be LTI systems. Okay, and we are going to do some questions on that. Okay, so I'll be giving you system and we have to find out whether that system is linear or non-linear or it's time invariant or variant. Okay, and causal or non-causal obviously. So okay, so this is what in control system what actually we want to do is that is given here. I hope you have covered this course or seen at least those videos. Okay, so basically what are the problems that we are going to cover in this. So what is synthesis? Synthesis is okay. So you're given with input and output, and you have to find the plant or the system. Okay, then that is the problem of synthesis. Okay, if you don't know the mathematical model, you know the input, you know the output. Okay, let's suppose you have some system. Okay, some system means let's suppose let's take an example of a circuit. Okay, let's suppose we have a circuit and you're giving the input and you're measuring the output. Okay, you're measuring the output through using various sensors. It may be current sensor, voltage sensor, anything. And you know what is the input. So input can be voltage, so you are giving the voltage. Okay, and you're measuring the current. Okay, so you know what both these things, but you don't know what is there in the system, how to model the system. Okay, that problem will be the synthesis problem. Okay, and the problem number two is, you see this problem, you are given the system, you are given the mathematical system and the input. Okay, you are finding the output. Okay, so basically you're finding the response of that system based on the input. Okay, once you have the system, different inputs you can give and you can find out the response. Okay, that is analysis and prediction. Okay, that we do once the system is available. And third is, you are given with the system. Okay, and you have set some objective, right? You want to achieve a particular output. Then how should I vary my inputs so as to get that output? So that is the control, right? If you want to control the current here, you want to control this current here, what should be the variation in the voltage? Okay, so that is the control problem. Okay, where we develop a controller such that it will vary the voltage according to our set objective of fixing the current. That is the output. Okay, so this is whatever I was explaining, so that is being discussed here. Okay, so this is the control, right? This is the, if you see DC motor they have taken as a plant. Okay, we want to control its speed. Okay, by way, and what is its input? Its input is your voltage. Okay, so to get a specified speed, what you first, you're taking feedback here, right? You're taking the speed feedback through sensors. They can be very sensors, and with respect to reference. So suppose I want to have speed 1500 rpm, right? And you are measuring something around 1400 rpm. Okay, so there will be some difference, right? The error will be 100 rpm here. Okay, so based on this error, the controller will act and actuator will decide the voltage. So it will decide the voltage such that the output of DC motor will go from 1400 to 1500 rpm. Okay, so since we are using controller, this controller, we are able to achieve the target of 1500 rpm. Okay, so reference is this and this is the output. So this is the control has been achieved here, right? So basically different parts of control system, elements of control system. Okay, so you know, forward path and the feedback path here. Okay, so how do we study? Okay, linear ODEs. So if you try to make the mathematical, or you get the mathematical equations of this system, so basically we are time invariant system. So you'll get linear ODEs. Linear ODEs, ordinary differential equation with constant coefficients. Okay, you'll get this. And how to solve those? You'll get a transfer function and state space representation. Okay, so in this course you will be focusing in with this transfer function representation. Okay, unity feedback, if sensor gain is equal to 1, we'll have unity feedback, and if it's not equal to 1, we'll have non-unity feedback. Okay, so this control system problem, stability and performance, we are going to deal in the further weeks. Okay, so here we have this is one example that we have covered. Okay, spring damper system connected to a mass here. Okay, so this is the equation here. Okay, so this is the equation. So this equation, you know, this is we have considered this as linear time invariant system here. Okay, so that's why you can see this is linear ODE with constant coefficients here. Okay, so this is KT. If it is constant, it does not depend on T. This MC, these are constants. Okay, let me just highlight this. These are constants, and if they do not depend on time, then I'll say this is ordinary differential equation, okay, with constant coefficient, okay, and this Ft is the external force, okay. Okay, so here we have shown how if the k is constant, okay, then it is ordinary differential equation, and if k is not constant, then it is time varying, okay. If your xt, if this term comes here in the equation, then it is nonlinear equation, okay. So that already we have seen, and how to linearize it, that will further study, okay. So some mathematical preliminaries that you need to know, because anyway we'll be doing mathematical analysis of the system then. So the important thing is you should know the Laplace transform here, okay. So about the ordinary differential equation and Laplace transform here, okay. So that's been covered, so I'm not covering, okay. So basically three type important, few important inputs here. So first is unit impulse, okay. So direct delta function. Second will be unit step. So we are going to cover this extensively in the course, and others are last one category of inputs will be sinusoidal inputs, okay. So we are going to see the frequency response of that, okay. And control, just the definition here for the control system, control design, stability and performance, that we are going to study in more detail in the further weeks, okay. So bounded input and bounded output, both stability here. So suppose if you are giving, if if for a given system, if you are giving bounded input, its output should be bounded, okay, for the stability. So that is the necessary condition here. So that is mentioned here, right? So then we studied about the Laplace equation, okay, initial value theorem, final value theorem. It's very simple, okay. And these are some of the Laplace go-to functions where you have to remember the Laplace transform of these functions. Very important here. Okay. Okay. The inverse Laplace. So we can get the inverse Laplace by using the definition of inverse Laplace, but we'll not be using. We'll be using polynomial functions here. Okay. Factorization and all these things, and to get the inverse Laplace transform. So some example is shown here. Okay. So, okay, this is the exercise that was given at the end of the week. So, just want to ask you, have you covered it? You want me to cover this? Okay, this one. Okay, let me do this. I don't know whether you have gone through this problems or not. That was given at the end of this week. Okay, let's do it before jumping on to the main questions of previous semester. Okay, so I hope you know the this basic Laplace transform of basic function here. Okay. Okay, by using that we'll cover these questions here. Okay, so the first is this one, a 1 by s square plus 2s plus 2. Okay, so let me do the first question for you. Okay, so I can write this as square, okay, plus s plus 1 square plus 1. Okay, can I write this? See, s square plus 2s plus 1. So I can write this way, right? So you know Laplace transform of sine omega naught t. So what is that? That is equal to omega naught x s square plus omega naught square, right? So in this, so if we consider omega naught to be equal to 1, then that is equal to 1 by s square plus 1, right? So this is the Laplace transform of sine t, okay? And we know here, if you see, okay, so we have done one question with, if we just multiply f of t with e of at, then in the Laplace transform you'll get s plus a, right? This, okay, this property will use this here. Okay, if then e of t, okay, sin t should be equal to, so coefficient is 1 here, so I'll just mark it here. So this coefficient is 1. Okay, so it should be equal to s plus 1. Okay, whole square plus, right? See, it's matching. Okay, so what is the inverse Laplace transform of this? Is equal to this one. If you say inverse Laplace transform of square plus 1, which is also equal to 1 by s square plus 2s plus 2 e of minus t sin t. Okay, I hope you're getting it. So this is the first simple question that was given to you. Any doubt in this? Okay, so you can ask me any A, B, C, D, E, which one I should solve. Okay, because these are very simple problems. Okay, so I'll just cover whichever that you are facing problem here. Okay, the D part you said, let's cover the D part. That is s by s square plus 1 whole square. Okay, so this is okay. So let me see which one we can use here. Okay. So let's write this s square s by. Okay. So you know Laplace transform of sin t. What was that? 1 by s square plus 1. Okay. Okay. Once again. Sir, you'll receive these notes. Yeah, I'll upload whatever, and this I will not solve. So I'll be solving previous year semester, previous year questions. So that I will upload. Okay. So you know Laplace transform of sin t is equal to 1 by s square plus 1. Okay. So let's use some of the properties here. Okay. So can we use this t into sin t? I think I'm making this mistake. Okay. Okay. So I'll just cover this question. Okay. Before that, I want to cover some few things. Okay. At the last, I will cover. So some questions based on linear and non-linear systems, and time invariant and variant system, causal and non-causal. So I'll cover those questions, and first let me cover the previous year or the previous semester questions first, because that I need to cover this here. Okay. So first one, causal system is always, so you know it is non-anticipatory, but few these are some questions here. So I just want to ask you, okay, whether these systems are causal or not. Okay. So what about the first one? Can you answer those, causal or non-causal? So we'll repeat this for the linear, whether the system is linear or non-linear also. Okay. The causal system is always, you see, the input and output. If you see the relation, the output is only depends on the present input, right? So this is causal. Okay. So first one is simple, it's very simple. Okay. Second one, if you see, so this is conjugate, right? Okay. This is conjugate. What can you say about this second option? Y of t equal to x of conjugate, whether this is causal or not. A causal system should depend on past inputs and present inputs, right? It should not depend on future inputs. So do you see future inputs here? Okay. So you can put any value. Let's suppose this is continuous system. Okay. So I want to find what is happening, what is the output at time equal to 1 second. Okay. So you see, so I need this one. Okay. So this is the input at time equal to 1 second, right? So this is present input. Okay. So if I want to find the output at different instants, then I need input at that instant, not the future instance, right? So that's why this system is also causal. Okay. What about this one? This is very interesting. Y of t equal to x 2t plus 3. Okay. Okay. I'm trying to get the output at time t equal to 0. Okay. So I put t equal to 0. You see x 2 into 0 plus 3. Okay. So this will be x of 3. You see. So I want to get the output at t equal to 0, but this is input at t equal to 3, right? So this is future. Okay. This is output at t equal to 0. And this is input at t equal to 0. Okay. So what can I say? This is non-causal, right? Because my present input depends on future inputs. Okay. The third one is non-causal. So similarly, what can you say about the fourth one? Okay. If you put y equal to 0 and then x equal to 0, that is fine. So let's put y equal to 1, then x is also equal to 1. If I put y 2, so I'm trying to find the output at t equal to 2, then x is 2 square is 4. You see here. So the output at t equal to 2 depends on input at t equal to 4. Okay. So what can I say? This is also non-causal. Okay. Okay. So what can you say about this fifth one? You see, whether it's causal or not, x of t or y of t equal to e raised to power x of t. You just put values. Okay, so this is also causal, right? Because it depends on present input. Okay, similar is with the sixth one. Okay, so this is mod. Okay, so y of t depends on input, present input. So this is very interesting. The seventh. What can you say about this? Just try to put different values of t and then find out. whether the system is depending on future inputs or not. Okay, let me check at non-causal you're saying. Okay, let me put t equal to, let's put 3. Okay, so this is t, 3 plus 4 is 7. Okay, 7, this is 7. Okay, so t at time t equal to 3, it depends on past. So x of 0 is past, right? So up to now the system is causal. So let's increase t. So I'll put t equal to 6. If I put t equal to 6, then 6 plus 4 is 10. X 6 minus 3 is 3. Okay. So you can see here, if I put different values of t, or increase the values of t, you'll find that it always depends on past input, right? So this is t equal to 6, right? So we are trying to find out the output at t equal to 6. So the output is depending on the input at t equal to 3. So this is past. Sorry, yeah. So this is past input, right? And in our definition of causal system, the input can depend on past inputs, right? Only it should not depend on future inputs, right? So this is causal system because it is t minus 3, right? Causal. So any doubt in this case? You put different values of t and find out. It always depends on past input, and that is there in the definition of causal system. Okay. Okay. So here it is very interesting, the eighth part. Y of t equal to x of sine t. Okay. X of sine t. You have to see whether it depends on future or not. Okay. So we can put different values of t here. Let's put 0. Even we can put 0, pi, 2 pi here, minus pi, 2, minus 2 pi, anything. So, because you know these values here. Just tell me. Okay, let's first put minus 2 pi here. Okay, so minus 2 pi, sine of minus 2 pi is equal to, it is equal to 0, right? It's sine minus pi. Okay, I'll just 0 pi and sine 2 pi. So it's all equal to 0. Okay. Okay. So so I have written this sine of, okay, write it properly, sine of minus 2 pi, so which is equal to sine of minus 2 pi is equal to 0. Okay. So I'm trying to find the time. I'm trying to find the output at t equal to minus 2 pi. But you see whether it's future or not, x of 0, just by seeing this expression. I can also put 2 pi. Okay, x. It will be simple if I take t equal to t greater than 0. So sine of 2 pi. Okay. So sine of 2 pi, is equal to 0. Okay. You see, at t equal to 2 pi, it depends on x of 0. Okay, so x of 0 is past. Okay, so you can say here, by looking at this, you can say the system is causal, right? But what can you say here? Is this future or not? Y of minus 2 pi, because if you say time, okay, so I'm trying to find out, this is, let's suppose this is t here. Okay, so this is 0, so I'm trying to find out the value here, but I need input of this point x of 0. Okay, so this is future, right? Because I'm analyzing the system as at t equal to minus 2 pi, right? So this is non-causal. Any doubt in this case? Okay, then we'll go to the second question. Okay, a system whose governing equation is yt equal to t into ut. Okay, so we'll do this question at the last. First we'll do few similar questions where we have same questions, but we'll find out whether the systems are linear or non-linear. Okay, you know the definition of linear and non-linear. So if you put, let's suppose we have a system, and if you give x of t, then your output is y1 of t, and if you provide input as x2, then you'll get output as y2. Okay, and third input that you can do is linear combination of these two. Okay, so a into x1 plus b into x2, and you will get y3, and your y3 should be equal to a y1 plus b y2. Okay, then you will call this system as linear system. Okay, so this is superposition principle that we are using it. Okay, so let's use it here for this particular system. Yt equal to root of xt. Okay, so first I will do this first one for you. So you know, if I get x1t, okay, as input, so output I will get output as x1t, right? Similarly, if I provide x2, I'll get this x2. Okay, so this is y1 of t, and we can say this is y2 of t. And if let's suppose I will give this x3t, just a x1t plus b x2t, right? Now this x3 is my new input. Okay, I'm giving to this system, so what should be the output? So the output of this is equal to y3t, which is this a x1t plus b x2t, right? Okay, so this is y3t. Okay, and it should be, if this system is linear, it should be equal to this a x1t plus b root of x2t, or you can say this to be y1 of t plus b y2 of t. Okay, you just compare these two values here, this one and this one, whether they are equal or not. Okay, they are supposed to be equal. If they are equal, you can call this as linear system. Okay, but here it is, they are not equal here, so this is again a non-linear system. Okay, so I've done the first one, so we'll do the second one here. Okay, space is not there. Okay, I'll do the second one right here. So y of t is equal to x conjugate t. Okay, similarly, I'll do this one also. For x1t, what is the output you're getting? X1 conjugate t, right? For y, for x2t, you're getting this as output x2 conjugate t, right? And if I give x3t, which is a x1t plus b x2t, okay? So what should be the output? Okay, now the output should be equal to a x1t plus b x2t, okay? So this conjugate. So just bring, let's bring this conjugate inside. It should be a star x1 t plus b plus 2t. Okay, so this I can write. Okay, let's simplify here. This is equal to y1t and this is equal to y2t. Okay, so I can write a star. Okay, so this is the result I got when I put this x3t, right? But what should I get? If this is linear system, I should get this a xt plus b x2 conjugate t. So this is the response I was expecting if this is linear system. B y2 t. Okay, I just compare these values here, this one and this one. Okay, and let's add this condition: a and b are complex numbers, right? If these are reals, then a star means same. Okay, I'll just write here a b are complex coefficients. Okay, so these are not equal, right? So this system is also non-linear system. Okay, given the condition a and b are complex coefficients. If these are real numbers, then you know if okay, right, if a and b are real, so what will happen? A is equal to a star, right? Simple. Then they are linear. Okay, but a and b are complex coefficient. That's why system is okay. This is non-linear. Okay, and I just erase this condition. Okay, so this is how we do. So I've done two parts, so let's do the third part. It is very interesting. So yt is equal to x2t plus 3, I think, yeah. x2t plus 3. Okay, you just try to solve. I'll solve here whether the system is linear or non-linear. So we're given with this. Okay, okay, for x1t, okay, I should get this 2t plus 3. This is y1t. Similarly, if I could give x2, I should get x2 2t plus 3. So this is y2. Okay, so now I should give x3, which is a x1 t plus b x2 t. Okay, just to test whether the system is not linear, non-linear. So what is the output I should get? So y3t is, okay, what I'm getting this. See, so this is different from the earlier first and second. So I'm getting this, I'm giving input as this. Okay, and you see the output what I'm getting. Just do it by yourself and see whether this is correct or not. So yt is x 2t plus 3, right? 2t plus 3. Okay. So whatever variation is there, that is on time, right? It's not on x. So let's see the previous one. You see the operation. So the first one, it was square root of xt, and in the second one there was conjugate of xt, and here it is just xt, but t is just 2t plus 3, right? And we are finding out whether this is linear or non-linear, right? So there is no what you call mathematical operation that's happening on x. Okay, so this is linear. So it's linear. So this problem you will encounter in the further weeks. So this is linear. Okay, you'll get more clarity if you do some questions here. Okay, so there. Okay, so let's do. I think fourth one. As you can see, square term. Okay, so you can straight away say this is non-linear. Okay, okay, and this one. Okay, this also you can say non-linear. Okay, because you try to solve for x1t, you'll get sine x1t. Okay, this is y1t, and for x2t you will get sine x2t, which is y2 of t. And if you give this x3t, which is equal to a x1t plus b x2t, okay, then what you'll get sine, okay, this one, so t plus b x2t. Okay, but what for the linear, what you should get this a sine x1t plus b sine x2t. You see this, these two should be equal for linearity. Okay, and they cannot be made equal, right? So this is also non-linear. Okay, so other, you see, this is again very interesting. Let's cover this 5. Y of t is this. Okay, if I give x1t, then the output is this, which I'm calling y1 of t. And if you give x to t, then this is mod of x to t. Okay, so I'll give a x1 t, this is x3. Okay, so what I should get should be a x1 t plus b x2 t. This is what I'm getting if I put this. Okay, but for linearity, what you should get this a x1t, this one, plus b x2t, or you can write a y1 of t plus b y2 of t. Okay, you have to compare these two. Are they equal? You see, they're not equal. Okay, I cannot just bring the mod inside this. Okay, so this is also non-linear. Okay, now it covers the sixth part. Sixth part is also, yeah, this one, six. This y of t is xt square. Okay, so again I'm giving input x1t. Okay, so I'm getting this x1t square. Okay, okay. x2t, so I should get x2t square. Okay, so this is now if I go x3, which is equal to x1t plus bx2t. Okay, so what I'll get same a, just this, you see, because they're doing the operation on x. Okay, you see here. Okay, this is also three. So and for linearity, what you have to write? You have to write this y1 a x1t square plus b x2t square, which is also equal to a y1t plus b y2t. Okay, and these two are equal. So there is also linear. Similarly, if you solve the seventh one, seventh is yt x of x sin t. Yt x sin t. Okay, so there is no operation on x. Okay, that is inside. Okay, you see sixth problem x t square, seventh is x sin t, and the previous one that we have seen x 2t plus 3. Okay, this will also be, if you solve this will also be a linear one. Okay, let me solve this. You will get what x1 sin t, which you can write y1t. Okay. For x2t you will get x2 sin t. Okay. So I will give x3t, which is linear combination of 1 and 2. Okay. What do you get? You'll get the same a x sin t plus b x. So this is x1. This is x2 sin t. Okay. So you can write a y1t equal to plus b y2t, which is same. So this is linear. Okay. You just see. Okay. First one was non-linear because there was a square root. Second one conjugate on x. Third one no operation on x. Fourth one x square. That's why it's non-linear. Fifth one, we are doing the mod of x, right? So that's why it is non-linear. And sixth one, you see, there is no operation on x. Again, 7, there is no operation on x. So that's why both are linears. Eighth one, okay, there was, because we have sine and the argument is x of t. That's why it's non-linear. Okay. So any doubt in this? Quickly I will cover the time invariance also. Okay, time invariance is, x of t, y of t. Okay, and what do you do if you just displace time t by t by this t naught? So I'm using this delay t naught. Okay, so you'll get output as y1 t. Okay, which should be equal to this y t minus t naught. Okay, so I'll just do the question and we'll see how I'm doing this. Okay, let me do the first one. Let me find out whether this is time invariant or not. Okay, so yt equal to root of xt. Okay, so I'm just delaying the input by t naught. Okay, so xt, I'm just delaying it, okay, by t naught. So this is xt minus t naught. Okay, so this you can say this is y1 of t. Okay, I'll write in this form. So my x1 t is xt minus t naught. Okay. Okay. So what is the output? Output is xt minus t naught. Okay. So I'm just using the definition that I mentioned above. Okay. So if you delay the output, put t equal to t minus t naught again here in this equation. So what you will get, t minus t naught is equal to root of xt minus t naught. Okay. So this one is, okay, this one. Okay. If we change the color, and this one, so let me call this as y1 of t. Okay. So this is also equal to this one here. So I have to see whether both are equal or not. If they are equal, I'll call that as time invariant system. So you can see y1 of t is equal to yt minus t naught. Okay. So that's why this first one is time invariant. Okay. First one. So let's also do for the, okay, let me do sequentially. For the conjugate part. Okay. Yt equal to x of t. So what I'm going to do, then I'm going to delay the input by t naught. Okay, so I'll just call this, okay, if I delay what I'll get t minus t naught, that I'll call y naught of t, y1 of t. Okay, so this is first. Then I will replace t equal to t minus t naught in this equation. Okay, so y t minus t naught is equal to, again, this one. If you see equation 1 and 2, both are equal. Okay, then I'll say this is time invariant system. So okay, let me do, you'll get more clarity if I do the time variant. Okay, let me do the fourth one. You can do the third one. Let me do the fourth one. Okay, so fourth one is y of t equal to xt squared. Okay, let me delay the input by t naught. Okay, so what I'll get x t square minus t naught. So I'm delaying the input by t naught. Okay, so this is y1 of t. Okay, now what I'm doing, I'm just replacing t by t naught in this equation. So t minus t naught is equal to x t minus t naught. This is whole square. Okay, okay. Known to write here again two times. So if you see these two equations, 1 and 2, okay, see this, they're not matching, right? Okay, so I got this one, put t equal to t minus t naught. Okay, so in the first one, what I have done here, delay the input by t naught. Okay, just by minus t naught I put. So these are not equal. So this is time variant system. Okay, but this is linear system that we have seen. Oh, there is no operation on x. Okay, so this is linear system but time varying system. Okay, so let me do one similar example, xt square. Okay, okay, so which one I should do? So let's do this fifth one. Okay, let me do fifth. Y of t is e of x of t. Okay, let me delay the input. Delay the input, what you will get? E t minus t naught. Okay, this is also linear. So this is y1 of t, and if I just put t minus t naught in this equation, I will get e of x t minus t naught. Okay. This is linear system. Okay, time invariant system. So we have not found out whether this system are linear or not. You can just use the whatever we have studied here in the previously when we are finding out whether the system is linear or not. Just do the analysis for this particular thing and you will find out whether the system is linear or not. Okay. So this is, but we have found out this system is time invariant. Fifth one. Okay. So what do you want me to find out? Sixth one is again, okay, let's find the sixth one. Sixth one is simple. This is time invariant. Again, directly you can look and tell. Okay. Now the seventh one, sine x of t. Okay. Just delay the input by t naught. This is again seventh. Let me do seventh here. Yt equal to sine x of t. Okay. X of t. Yeah, this is very tricky. What you are doing, you are delaying the input by t naught. Okay. So how to delay the input by t naught? Here. Should I put this sine xt minus t naught? See the argument, that is sine. Or can I do this sine x t minus t naught? T minus t naught. Okay. Can I write this? Which one is correct? The first one or the second one? So we have found out the system is non-linear, right? I think in the previous one when we are doing this one x of sine t. Okay, this is okay. Okay, we have not done. I think for the sine we have done sine of x of t. This is non-linear. Just trying to find out whether that is time invariant or not. So this is non-linear. We have found out. So which one is correct? See, first is xt minus t naught. So can I say this is delay or not? Like when I do this xt minus t naught, is this delaying in time? Or this one is delaying in time? Okay. I think the second one will be correct. This one is correct, right? Just see second part. Okay. So we are delaying the input, right? How to delay the input? Xt minus t naught. Okay. This is you're subtracting something from the input, right? X of t is input, and we are subtracting something. So I'm writing minus t naught, but it is like subtracting something. So it is not delaying in time. Okay. So this is also linear. Sorry, it is non-linear, but time invariant system. Okay. Okay. So let's do the main question here. Okay. So a system whose governing equation is yt equal to t into ut. Okay, t into ut. So this is our xt. Okay. So okay, let me do it the last. The question is second question is yt equal to t into ut. Okay, let's first check for the non-linearity. Okay, so directly you can tell because you know we are studying in the course also. Okay, but first let's do the mathematical, like how we have seen for the other systems. Okay, for non-linearity, you know, if I give u1t, t into u1t you will get, okay, this is y1t, this is y2 of t. Let's me give this u3, which is a u1t plus p u2t. Okay, so the y3 will be t a u1t plus p u2t. Okay. So it will be same a t u1t plus p u2t. This, you know, this is what, this is y1t, okay, and this is y2t. So this is linear combination. So the superposition principle is applied here. Okay, so I can say this is linear. So linear. So let's check whether it's time invariant or not. Okay. So let me just delay the input. Okay. First delay the input. If I delay the input, what I'll get? T y t minus t naught. I'm just delaying the input, right? Y1t. Delaying the input. You know, this is input. Okay. But if I put t equal to t equal to minus t naught, the entire equation what I'll get t minus t naught u t minus t naught. Okay, this is y t minus t naught. And you just compare these two results here. This one and this one. Okay, these are not equal, right? So this is time varying. Okay. So directly you can just say, because you know we are studying in linear ODE also, the coefficients. So this is coefficient, okay, which is varying with time. Then we say time varying system, right? Directly you can tell, but we have done the analysis and we have found out it is linear time varying. Okay. Okay, this is linear time. This one is correct. Second. Okay. Let's quickly go to the other questions. Okay, consider a washing machine unit to which an electric current is provided as input and the rotational speed of the drum is the output. Okay, so we have a washing machine. Okay, so input is your current. Okay, so this is the current and the output is speed of the drum, rotational speed. Let me call it omega, which is in RPM, right? Okay, if then one wants to find the mathematical relation between the electric current input and the drum rotational speed output, then one is solving the problem of, obviously, this is synthesis, right? Okay, you know the input, you're providing the input and you're finding out the output, but we don't know the system. Okay, so you want, if you want to find the mathematical relationship between the output and the input, and that problem we'll call it as synthesis problem, right? That we have seen. I think there will be no doubt here. Which one of the following is an example of open loop control? Okay, again we have seen, okay, ceiling fan, right? And every other we have feedback control, right? So in servo motor, you know, water tank level, we always have a sensor in all of the above three options here. Okay, in air conditioner you want to set the temperature to particular value. Okay, so constantly temperature sensing, temperature sensor is sensing the value, and if it is the temperature of the room is above or below that, then it will get the feedback, and what is happening will control the current or voltage. Okay, so as to maintain the temperature. Similarly with the other two cases. So the ceiling fan that you're seeing, when the mapping in the feedback path is not equal to 1, it is called, again this is very simple, unity feedback, right? So sensor dynamics, if we neglect sensor dynamics, we call it unity feedback.
It's not equal to 1, right? It's non-unity
Oh, and
feedback.
the mapping in the feedback path is not equal to 1. Okay, okay, sorry. This is non-unity feedback, correct? You're correct. So in this, if we take the dynamics of the sensor, then it's a non-unity feedback. It is like HS is not equal to 1. I don't know whether you have studied this GS is the plant. Okay, let's not go into HS and GS. We'll see in the in next tutorials. Okay.
Okay.
So in a typical closed loop system layout, okay, the element that takes the controller output and realizes the same to provide it as the system input is called as, okay, so you know this is controller and the plant. Okay, so in between you have something. Okay, this is controller. And let's take unity feedback. Let's, okay, so this is the reference plus minus and this error. Okay, so sensor is here. So this is sensor, everything. So this is plant, this is controller, sensor is here. Okay, so the actuator, right? The element that
Yes.
takes the controller, okay, controller output and realizes the same to provide it as system input. Okay, so in ideal system, it take actuator gain as well as the sensor gain to be equal to 1. Okay, that we will see further in further classes. So this is actuator, correct. So that dynamics of the element that measures the output of the system and provides feedback is called. Again, same diagram we can refer, right? So this is the output. Okay, so let me call this as RT reference. So it says the dynamics of element that measures the output of the system and provides feedback. Okay, so this is providing feedback here. Okay, so sensor is providing feedback. Okay. So it's called sensor dynamics, right? Simple. Actuator dynamics, sensor dynamics. The class of linear time varying causal CISO dynamic system is typically characterized by, you see, linear time varying. Okay, so you're seeing time varying means we'll have coefficients which depend on time, right? So those will not be constant coefficients. Okay, so that is linear ODE with time varying coefficients. Okay, okay. So we have seen in the previous one example also, right? T into UT problem. Okay, so this problem we are doing T into UT. Okay, so the coefficient is time varying. So this is like not ODE. Okay, not a differential equation, but okay, linear ODE with time varying coefficient that we have seen in the lectures also. We'll go further. Ninth, a mass spring damper system is governed by the equation. The system is, okay. So you see here. So let me just write in differential. This is this equation. Okay. Just focus on this part here. Okay. So it's a linear combination of input and the differentiation of that input. Okay. So this is what, linear or non-linear? Okay. This is not coefficient. Your coefficient here are x itself. Okay. This is coefficient. Okay. So this will be non-linear. Just see xt into d of xt. Okay, this one, because of this second part, second means xt into dx by dt. Okay, this part is making this as non-linear. Okay, so see t, everything is fine, but this part is making it non-linear here. Okay, like this is non-linear part. Okay, so the other variants can be this xt dt plus, let's suppose we have some coefficient k t that we have seen in our course. Okay, plus xt. Okay, so this is linear, right? But this part is making, this is linear but time varying. Okay, and again one variant is, if I write this plus k, just constant dx by dt plus xt equal to f of t. This is again, this equation is linear time invariant. Okay, so you've seen the combination, all three combinations in the course also. Okay, very simple. Okay, 10th problem is the complex function is singular at, try to find out the root of this. Okay, so okay, let me write gs as 1 by s square plus 2s plus 1. Okay, again you can see it can be written as s plus 1 square. Okay, so when this gs becomes infinite at s equal to minus 1. Okay, analytic function or not, that also we have seen the definition of this. Okay, so this function is singular at point s equal to minus 1. Very simple. Okay, the Laplace transform of this function is, okay, so you know Laplace transform of sine t. Okay, 1 omega naught is equal to 1 here, s square plus 1. Okay, now okay, here if I put omega as 2, then this is equal to 2 by s square plus omega naught square, which is equal to 4. Okay, and e of minus t, if I put sine 2t, okay, this will be 2 s plus 1 square. Okay, so it is like e minus at, okay, where a is equal to 1. Okay, so that's why s plus 1 square plus 4. If you simplify this, you'll get s square plus 2s plus 1 plus 4. Okay, what you can do, you can write this as plus 5. Just 2 by s square plus 2s plus 5. Okay, simple question. So 12, 15. Consider the LTI system whose governing equation is this. Okay, so let me write the equation. Plus 3 dy by dt minus 4 y of t equal to u of t. Take the initial condition to be 0. Okay, all the initial condition y of 0 and this one is equal to 0, and you know this is ut is step input. Okay, step input. Okay, you know step input, right? Step input is like this. So let's, so it is t equal to 0, we are providing some constant, so this is unit step. Okay, and the magnitude is equal to 1. Okay, so this is unit step. Okay, the value of output as time tends to infinity. So let's first convert, let's find the Laplace transform. Okay, you know Laplace transform is s square y of s, okay, minus what you call y of 0 minus ey. Okay, so this is d at t equal to 0, okay, plus 3 s y of s minus y of 0, okay, plus minus 4, okay, y of s, and this is u of s. Let's not first write 1 by s. Okay, so this is, initial conditions are equal to 0. Okay, this is 0 and this is also equal to 0. Okay, so let's simplify it. Square ys plus 3 sys, okay, minus 4 ys equal to u of s. Okay, let's take ys common. So this is 4 u of s. Okay, so this is multiplication. If you put ys by us, you'll get the transfer function, what we'll call transfer function. Okay, so this is us by x square plus 3s minus 4. Okay, so what it says, the value of output as time tends to infinity. So you have studied two theorems, right? Initial value theorem and final value theorem. Okay, so what you want to find out is t. This you want to find out. Okay, so what we can do, which is also equal to s tending to 0, s into ys, right? You studied the theorems, right? So you can use this, because what it says, the value of output as t tends to infinity, right? So limit t tends to infinity yt, which is equal to limit s tends to the 0, s into ys. Okay, final value theorem, because we are finding the final value of y of t when t tends to infinity. So let's find out s into us by s square plus 3s minus 4. Okay, so it's a step response. That means us is equal to 1 by s, right? Laplace transform you've seen. So I'll just write, okay, if you find the Laplace transform of u of t, you'll get 1 by s. Okay, so this information we are using here, square plus 3s minus 4. Okay, if you put the limit, you'll get minus 1 by 4. Okay, this is, I think, minus 1, 0.25. You'll get this minus 0.25. Okay, so the first option is correct, right? I think this is also very simple. You have to find the Laplace transform, okay, then apply the theorem. Okay, very simple. And if we put s equal to 0 limit, if we apply the limit, you'll get 1 by minus 4, which is equal to minus 0.25. Okay, very simple. So let's find the coefficient of t, e of t in the output function. Okay, so this is our output. Okay, okay, let us first solve this, try to find the solution of this. So ys is us by x s square, us square plus 3s minus 4. We'll use us as 1 by s, right? So this is like 1 by s square plus 3s minus 4. Okay, so let's find the factors here. Okay, this, what are the factors? Can you tell me? 1 by s, okay. So the factors are this plus 4. I hope I'm doing correct. I'm correct here. Okay, let me check it. Okay, okay. So this is 1 by s into s minus 1 s plus 4. Okay, so this is y of s, right? Now let's find the inverse Laplace. So we can write this as a by s plus b by s minus 1. Okay, that we have seen in the lectures also, how to solve these types of problem. Okay, so first is this. Okay, so how to find a? Multiply this ys by s. Okay, so I'll do the first part, second I'll write t, right? Okay, and you're writing this part as s minus 1 and s plus 4 as a by s plus b by s minus 1 by c s plus 4. Okay, to find the value of s, what do you do? Just multiply both side by s. Okay, so you'll get this side s minus 1 s plus 4. Okay, a plus bs by s minus 1 plus cs by s plus 4, and put s equal to 0, right? To put s equal to 0, what you'll get? Minus 1 into 4, and this term b and c term will be equal to 0 because numerator is equal to 0. You'll get a is equal to minus 1 by 4. Okay, you know the process. A is minus 1 by 4. Similarly, if you do the same thing with b and c, okay, directly I will write, we write b. Okay, let's do the b. For b, what you do, I'll write this as equation 1. You multiply equation 1 by s minus 1. Okay, so what you'll get here is into s plus 4, right? Equal to a s minus 1 plus b. Okay, this will be there, c into s minus 1 by s plus 4. Okay, and you put s equal to 1. Simple. You put s equal to 1, this is 1 into 4, which is equal to b, because numerator of this term, so if you see this term and this third term will be equal to 0. Okay, so b will be equal to 1 by 4. Okay, similarly if I do for the c, multiply by s plus 4. Okay, so I'll get this, multiply equation 1, so this is equation by 1 by s plus 4. This is plus 4, this is s minus 1 plus c, and put s equal to minus 4. So you'll get minus 4, and here you'll get minus 5. Okay, minus 4 minus 1 is minus 5, and a and b, they both are equal to 0, and c is equal to minus 1 by 5. Okay, so abc, I'll just write the equation 1. Okay, just fill the coefficients here. So writing equation 1 as a is minus 1 by 4 by s plus b is 1 by 4 by s plus c is, so this is 20, right? 1 by 4 into 5. Sorry, this is minus 1 and this is s plus 4. Okay, so this is y of s. If you try to find the inverse of this, you'll get, minus 1 by 4, okay, plus 1 by 4 into e by t, right, plus 1 by 20 e of minus 4t, right? So this is the final solution that you're getting for the transfer function, right? So what they have asked is the coefficient of e raised to power t. Okay, so it should be e raised to power t. So they are asking me to find this. So 1 by 4 is 0.25. If I am correct, I don't know. Okay, answer is think somewhere I made the mistake. The P part, okay. Okay, so I'm sorry. So in this case, what? S equal to 1. So you have to put S equal to 1 here, okay? So this was 5, right? S, so if I write this 1 plus 4, right? So which is equal to 5. Sorry, this is 5. So 1 into 5. Okay. So this is 5, 1 by 5. So 1 by 5 is 0.2. So this is correct. 0.2. Okay. So going quickly to the next question. The coefficient of r minus 40 is 1 by 20. Okay. 1 by 20. 1 by 5. Okay. This is equal to 1 by 20. 0.5 by 10 is 0.05. Okay. You see here 1 by 20. So 1 by 20 is equal to 0.05. Okay. Which one of the following statement is false? The output is bounded in magnitude for all time. Okay, for this above, okay, let me write the equation once again. So y of t is equal to 1 by 4 plus 1 by 5 e of t plus 1 by 20 e of minus 4t. Okay, for this particular output, we have to find out which one is false. Okay, the output is bounded in magnitude for all time. Okay, at t equal to 0, 1 by 4, at t equal to infinity, what is happening? At t equal to infinity, you see the second term, okay? This will become infinite. So the first statement will not hold. So output also becomes infinity, right? At t equal to infinity. So the output is not bounded in magnitude because it's going to infinity. So the first statement is wrong. Okay. Let me check the second. The only function of time that appears in the output function are exponential functions. Correct? Because if you see e of t and e of minus 40 both are exponential functions and they are function of time, right? So the second statement is true. The value of output function is 0 when time is 0. Okay, so let's find out. Okay, I will just write put 0. So if you put t equal to 0, then this will be okay. I think somewhere there was minus here. This is 1 by 20. Okay, so if you try to find out, this is 20. Okay, so this is minus 1 by 20 plus 1 by 20, which is equal to 0. Okay, so at t equal to 0, y of 0 is equal to 0. Okay, this is also true. The third option, the value of output function is 0 and time is 0, right? Correct. So the last option, the value of output is non-zero as time tends to infinity. The value of output is non-zero as time tends to infinity. This is correct, right? You know it's infinity and it is non-zero, right? So only option first is false. So any question in this? I think, yeah, these are the questions. Okay, any question? So whatever that I have solved here. I don't know whether for you the questions are same or different because I have not looked at those. So these are the questions that was for the previous NPTEL batch, right? So that was simple. So the first is basic introduction to the control system. So that's why basic about the type of system and the Laplace transform. So questions are based on that. Okay, so that's why. So any doubt in this today's session? Okay, so I'll be uploading this video as well as notes for today's session. Okay, so you just click on the link and you can find the notes and the video also. Okay, so any question for this assignment questions? If there are no questions, I will close the session. Okay, we'll meet in the next session. Okay, just follow the notification when is the next session.
Thank you.
Okay, thank you for attending this tutorial. Thank you.